So, we started with the random process. And now we know that what random process actually means. For every random process, just the same as random variables, we have the properties. We have statistics, the mean, the covariance, and several other useful statistics that we want to go through that in this lecture. And we want to go through the theory, the kind of application that uses these kind of statistics to get something. So there are two concepts in the random process, every random process, which are very important. And they are called autocorrelation function and power spectral density function. So we have autocorrelation and power spectral density. So in very simple statement, power spectral density is the Fourier transform or DTFT of autocorrelation function. So just one statement. The power spectral density, which is denoted by S, for example, for the signal X, for the process X, we say S of X, and it's random, it's an independent variable, is omega. So it's a Fourier transform. It has the Fourier, it's actually the Fourier transform of the autocovariance or autocorrelation function. That's the first idea. And that's based on the Wiener-Henshin theory. What these two mean, actually. We already talked about the mean and variance. We also have some more statistics. When we are talking about relations inside the data samples, the random variables, we speak about the covariance. So if we have a random variable xt, for example here, assume that it's xt and this is another random variable, it's s for example, then the covariance between these two, xt and xs, is actually represented by this expectation. But in the same way, we have the sample expectation for the autocovariance. If these two random variables belong to the same process, this result is called autocovariance. If these two random variables belong to two different processes, that's called cross covariance. So cross means between two different random variables or two random variables from different processes. But if in the same process you have two random variables and you're calculating the variance, the covariance between these two, it's called autocovariance. You got it? And the correlation between two random variables is covariance normalized. Normalized by the variances. Okay? These are the moments of random processes. In random processes, autocorrelation and autocovariance are two important entities. But the difference is actually very trivial. What is the difference between autocorrelation and autocovariance? The difference is clear here. Autocovariance is autocorrelation when we subtract the means. So here, for every random variable, so if it means that if you just take the expectation of this times this, you have the autocorrelation. If you centralize these two random variables around the mean. So it means that if you subtract the mean of the random variable from the variable, and mean of this random variable from this variable, and then take the autocorrelation, the result is called autocovariance. And this is the relation. So the autocovariance and autocorrelation, so autocorrelation, autocovariance, they have this kind of relation. Why we speak about autocorrelation, autocovariance? Because they have a very nice properties. Very nice properties. Before to go to the properties of autocorrelation and how to use that, we have a very nice theory which is called the WOLD Theory, or WOLD decomposition. We can hear both of them. In mathematics they call it WOLD decomposition. And Google it, there are very nice statements in Wikipedia you can find about the WOLD theory. In general, what WOLD theory says is written here. It says that any stationary process, so the first condition is to have a stationary process. If we have a stationary process, then that stationary process can be expressed as the sum of two components. One of the components, so it is a stochastic component or the random component, which can be represented as a linear combination of white noise processes, lagged. So if you have white noise with different lags, it's a stochastic process. So in general, it's combined as a sum of two different functions. One, a stochastic process, and the other one is the deterministic one. The deterministic component, which is uncorrelated with the previous one. So the deterministic component, which is uncorrelated with the stochastic component. And why it's so important, we will go through linear prediction model and we'll see that. But in general statements, it means that any random process which is stationary, it can be written as linear combination of lagged values of white noise plus a moving average system. So it means that if you have any kind of stationary random process, you can model that. You can model that as a white noise applied to a moving average system. I write it down as an LTI filter. And here you will have a stationary process called XL. White noise, white Gaussian noise, applied to a filter. Here is written moving average. It can be any other systems. And it will give you the stationary random process. Here is the stationary random process. So it means that, you know, it's a desire for every analyzer, for every processor, or for every human that tries to solve a system and the equations in the system, to have a model. If you can have a model, it's a point. If you can have a linear model, which is also time invariant, it's a bonus point. And it's actually giving you the bonus point because it means that you have an LTI system that you can just input to that LTI system a white Gaussian noise, and you can get any random variable, random process in the output, which is stationary. So the only thing is that if we know already that this process is stationary or not. then we can model it. Pay attention, please. I'm not telling you that this model completely characterizes every stationary random process. My statement is the other way. I'm saying that every random process which is stationary can be very good modeled using a kind of system like this. Can be modeled, can be approximated. So how it's the generation process of that stationary process, this stationary signal, the generation process can be modeled by the system, such kind of system. Very good. So one of the results of this WOLD decomposition in the mathematics is that it actually implies that if a process is stationary, we immediately know how to write the model for it. The only things that remains is that how to get the parameters of the model. That's all. So if we can get the parameters for the model, and what are these parameters? One parameter is variance of the noise, and the second portion of the parameters are those related to the system. And it depends how do you want to model the system, that's all. So parameters of the system and parameter of the white Gaussian noise, which is the variance of the noise, are the set of all parameters. If you can estimate those parameters based on the data, training data, then you model the data and you can have, for example, prediction. You can predict what's the next sample of the data based on all the previous samples. And that's the motivation for linear prediction. So the problem that comes out of that is we need to estimate a lot of parameters, probably. And it depends how do you want to approximate. For example, if we have a linear time invariant system with infinite number of the parameters, or we have a white Gaussian noise and we want to take infinite amount of samples, then that's the best case we can approximate that process. But we don't have access to infinite number of parameters. We have to restrict it to some certain amount of parameters. Those certain amount of parameters for the system is called order of the system. And the subject of the theory is called model order detection or model order estimation. Probably in the articles you see that. Model order estimation or detection for such system. It means you want to get how many parameters should be set for this system to get a good approximation of that process in the end. That's one statement about what the subject means. Okay. Now, very good properties for LTI models. So, based on the WOLD decomposition theory, we said that the stationary signal can be approximated with such model. We have a white Gaussian noise, nu of n, as the input of an LTI model, LTI system, with the DFT or the impulse response shown as h of something like this. And then you have the process, which is a stationary, random process. So here we have everything, all the signals are random. This LTI gives us many things. One of the things is that for white Gaussian noise, the only parameter is sigma square. And the power spectral density of the white Gaussian noise is sigma square. How they are calculated, I will write down on the blackboard as the time allows us. If I couldn't, I will provide a lecture, a video lecture auxiliary. I will attach it to this lecture and you can just get it from there. So every calculation. But the good thing is that the power spectral density in the output is the magnitude square of the system if the system is LTI. That's correct, only if the system is LTI. The output power spectral density is the magnitude square of the system, that LTI system, times the power spectral density of the input, which is white noise. And there are different models that we can assign here for this LTI. In general, if we could go through the chapter 5 of the DSP theory in Oppenheim book, we could have different models like the AR model, MA model, and ARMA model, which is a combination of both. But here I'll just explain very briefly these topics. If I can have time, I will just write down the face of the problem. So there are three different models we can assign here, and one of them leads to the theory of linear prediction and AR model, the stationary process estimation. We named it. So these two theories are almost the same. Linear prediction is very useful. In the next example, you'll see why. So we use one of these three, but our emphasis is about the first one, which is autoregressive model. Autoregressive model is an all-pole LTI system. So you probably know what all-pole means. It means that it's just including the poles and not any zeros. So a system is called all-pole, or AR, if it looks like this. So this is an example of all-pole system. We only have poles, and there is no zeros. In general, it's represented as, so the first coefficient is taken out as a constant and is written as 1, because if you just put it here, it's just getting 1 for this part. So it's also written as 1 plus k, 1 to the n, a k, z minus k. This is an example of an all-pole filter. So this autoregressive means the system should look like this. When we say moving average, it means that this should be gone here in the denominator. And when we say ARMA, it's a combination of AR and MA. So you have, for example, for ARMA, we have n number of zeros and n number of poles. Okay. If we try to write down the system containing this nu of n, or the white Gaussian noise, in the input, and this x of n in the output, using the AR model, it means that the system here is an AR model, then the form of the equation would look like that, the upper equation. From the equation, we get this filter, this AR here, the thing that we are replacing here, is an IIR filter. Why? Look at the equation and tell me why. This system and AR model, if I just replace it and then just using the time domain, we get that equation. And I say that this is an IIR filter. Why? Because in IIR filters, what? Output of sample n at every time depends on the outputs of previous samples plus the input. So output at time n, if in an equation we see the output of at time n and outputs of previous times n minus 1, 2 and so on, and here is the input, that means the system here is IIR filter. It's a kind of IIR filter. So, and here's the representation of that filter. We need to get the parameters to find out these AK parameters. If we can get AK parameters for this and the sigma square for this input, we have characterized the system completely. It means we have modeled a random stationary process. So, rewriting that statement on top, that equation, to look like this, xn plus or minus this form, and then trying to minimize. So here what we actually try to do in the linear prediction or AR modeling is we try to minimize the square of this. We consider this noise as an error, and what we try to do is to minimize the square of this error. The square of this error as a function of these AK parameters is quadratic function of those parameters. It means the resulting optimization problem is a convex problem. When a problem is convex, optimization problem is convex, if you can solve it, the solution to the convex problem, for example here the minimization, is not only the local minimum, it's the global minimum. So it's actually the real solution of the problem. And that's the good news about the convex optimization problems. That's why AR model is frequently used, because if you just use the AR model, if you only use the AR model, you will get this quadratic form, which can be easily solved and can have a unique solution in the optimization problem based on this AK. If you use the MA model or ARMA model, you will get something non-quadratic, and finding that solution for that is hard or impossible. And because it's not convex, then the solution is not unique. That's why in practice mostly we use the AR as the model of the stationary processes. There are several ways to find the solution to that equation I mentioned. One of them is using the autocorrelation function. And that's the point where I said that why autocorrelation function is very important. So in a very simple way, if we write it down based on the autocorrelation function, we will get these equations that you see here in the matrix form. So I can just write it down. I can write it down here. Just for one of the equations, and then for the rest we'll get it. So we had xn plus a1 xn minus 1 plus, in the end, a n or m, I don't know what it was, m x n minus n, the number of the parameters of the system, which was equal to nu of n. The solution goes this way. We need to multiply this equation with, first of all, x of n minus l, so both sides. And so on. And the next, the right hand side. Then we take the expectation again from both hand sides. Assume that L is bigger than 0, greater than 0. Now we take the expectations. Expectation of xn minus L. What is that? You're taking the expectation of signal or the random variable at time n with random variable at time n minus L. Autocorrelation. Right? It's autocorrelation. And if the signal was stationary, I said that autocorrelation is independent of time. N is the parameter of time. When the result is independent of the time, it should only depend on distance. So we write it down normally with Rxx or nothing. So if we know that the signal is x and we are taking the autocorrelation, the only signal is x. We can write down Rxx or nothing. So it depends. And here is Rxxl. So we know that signal is stationary. Because it's stationary, these are the properties of the stationarity of the signal. Because the signal is stationary, the autocorrelation of the signal at time n and time n minus L doesn't depend on time. That only depends on the lag between these two random variables. And that's the lag. And if you apply this fact to any of these terms, then the result would be RL, I just simplify it, I forget about this x, plus A1 R L minus 1 plus A M R R L minus m plus 1 or minus 1 L minus m. This is L, the other one should be L minus m. What is the expectation on the right hand side? I am calculating for L greater than 0. So I'm talking about the noise sample at time n, taking the expectation of noise sample at time n and signal at time n minus L. What is this autocorrelation? Or actually, it's better to say cross correlation, because we are taking between nu and x. There are two different random variables, two different signals actually. They are, I said that for the noise, is white Gaussian noise. What Gaussian noise means, every sample at every time, even with the adjacent samples, is independent. Even with its adjacent samples, that's independent. How come for another signal at time with the L lags, L times before, L samples before? So they are independent. When they are independent, their cross correlation would be 0. These two are orthogonal. They are independent. And orthogonal, if they are independent, they are orthogonal, then the expectation would be 0. So the right hand side is 0. If L is bigger than 0. If not, if L is equals to 0, then you just write down the x of n as the combination of, is actually nu of n convolved by the filter. So if you just simplify that, the only things that remains based on the spectral theory that I mentioned here. Output and the input. Here is the input, here is the output in the system. So the only relation here for the autocorrelation, if L equals to 0, the right hand side gives you the sigma square. It's the variance of the signal, the noise. So the rest of the thing on the right hand side is sigma square. Now, for different values of L, because we have, m parameters of the system, A1 to AM. For m parameters of the system, if we write down for L equal to 1, L equal to 2, L equal to 3, and so on until L equal to M. So here we have L. L should go from 1 to M to get M different equations with M different unknowns. Then we have this. We have this equation. This equation, and because the autocorrelation function is real, so the matrix that comes out of that is symmetric. So even though here you get R minus 1, but because of the reality of this autocorrelation function, R minus 1 and R1 are the same. For the real signals, the autocorrelation is real. When it's real, it means that it has the even property. So we apply that. I will go through that in the video, in the auxiliary video lecture, because we don't have time. I don't want to go to the properties of autocorrelation. The only thing is that the outcome as this matrix is the symmetric. So R1, here is R1, R2, R2, and so on. Rn minus 1, here is the same. And diagonality, you see that everything in the main, the diagonal elements are 0, and the adjacent vectors are R1, R2, and the same. And this kind of matrices are called Toeplitz matrices. They are called Toeplitz matrices. When a matrix is Toeplitz, it can be easily solved using Levinson-Durbin recursive algorithm. Just know that the algorithm is called Levinson-Durbin, and you can go to the MATLAB, write down the code, that's all. And this equation is actually called the Yule-Walker equation. So you have the matrices of the autocorrelations of the data. So that's the autocorrelation of the data. Times the parameter vector. These are the parameter vector that we want to actually get this. And these are the outcomes, the right hand side. So these are the autocorrelation values. So if you write, if we solve this equation, we get the A parameters. And just the matrix form. The matrix form of this is R A. This is R, the matrix there. R. This is A, and this is the vector R. So the result will be R inverse R. But getting that inverse is by using the Levinson-Durbin algorithm. When you get the parameters A, you just put it here, and for L equal to 0, you get the variance of the noise. So using the Yule-Walker equations, you can both get the A values, parameter values, and the sigma square, or the noise variance. And the entire system is characterized. Okay, let's go directly to the example. A speech production model, one of the famous models in speech theory is linear prediction model as the speech production model. I mean, a speech as a random signal, and considering this is stationary, can be modeled using the LPC. So it means that we have different phonemes. Part of the phonemes are vocal or are voiced signals. Part of them are not voiced. They are mostly like the noise, pseudo noise. For example, for the voiced A, E, U, these are voiced speech. They actually stimulate the vocal tracts. Then that's why they call voiced. So you will find some kind of resonances that come, with the frequencies and the harmonics. And part of them are mostly random, like the pseudo noise. Like s, sh. There is no activation from the vocal tracts. So that's why here you see a system with the switch. So if the phoneme, which is generated, is from the voice, you have actually the impulse train, and the impulse train comes with a frequency that depends on the frequency of stimulation. And if it's a random phoneme, as those belonging to the noise, so it comes from the random generator. But in the vocal tract, it's actually modeled as the AR model. This is an AR model with the P number of the parameters. And these are the AK parameters of the model. So it means that, in general, the speech in the output, this is the outcome. This is speech signal. Speech signal in the outcome, based on this system, and this is the random noise. This is the gain actually. So the speech signal is modeled as this filter actually, plus the input that you get from one of these two, times the gain. That part of the speech signal which belongs to, for example, the voiced or unvoiced part, that's something that just approximates the speech signal, is this filter part. So what we try to do is to get these parameters AK, and if we can get them, it means that we can characterize the entire system which produces the speech signal. And it means that I can somehow predict the next sample of the speech. And I can also, somehow in an optimization algorithm, I can, and for every stage I predict something, and then I get a new sample, and based on new sample, I can update my belief about the parameters. So why is that important? Because you're actually, in the normal case, if you want to transfer the information of a speech to someone, like the wave signal which is grabbed without any process. If you are doing, for example, 8 kilohertz of sampling, and for each sample you just dedicate 8 bits, it means that for every second of a speech, or for every frame of a speech, for every frame, you need, because it's 8 kilohertz times the 8 bits, it's 64 kilobits of data that you have to transfer from someone, from the one that you grab the signal and you want to give it to someone else. 60 kilobits of information. But now we are modeling that speech with just few number of parameters. And it turns out that for the speech signal, in general, that AK, the number of the parameters, wouldn't exceed 10 to 14 parameters. So it means that even using 10 up to 14 parameters is enough to characterize that entire model. And you can easily see that what happens if you for example code the speech with those parameters in the model. That's the basic idea of how speech compression happened. And coming from PCM with the MULA, that I already explained what MULA is used for in the sampling and the quantization. Using the sampling rate of 8 kilohertz, which results 64 kilobits of data. Now you go to the methods which use the LPC coding, using the few number of parameters as AK, and then you can have just 2.4 kilobits of data. So you can just see how much compression of the data you've made. So the data is compressed a lot. And that's called the LPC compression method. And it was used frequently in the GSM mobile, in the first generations of the GSM mobiles. They actually used the LPC code for compression of the data. So speech was not transferred using the PCM, but it was compressed inside the handset. It was compressed using the LPC method, and it was transferred because we actually needed to use the bandwidth of the data which is available for every person more efficiently. We cannot have that much large bandwidth for just one person. The channel capacity is limited and is restricted. So we can have, for example, 2 megabytes of bandwidth, and we want to give the service to as many as subscribers that we can.